Close your eyes just for a second and listen. I want you to imagine a low, heavy rumble growing louder. Picture this massive, cavernous, pitch-black turbine hall. Right in the middle, these colossal synchronous generators are just spinning, casting these giant moving shadows across tons of heavy steel and copper. This isn't just machinery. This is literally the invisible heartbeat of our entire modern world. Welcome to this explainer. Today, we are diving deep into the invisible, kind of cinematic physics that actually keep our electricity grids from completely collapsing into total darkness. So let's jump right in.
When you look out your window at those huge transmission towers, the power grid looks incredibly solid, right? It just seems so steady, completely unmoving. But actually, scratch that. It's really not. The truth is, the grid exists in this constant, super delicate state of tension. Deep inside that vast interconnected system, there's something completely invisible working tirelessly 24/7 in the dark to maintain a perfect, real-time balance between the power being generated and the power you're consuming at home. And that invisible force is exactly what we're talking about today.
That force is called inertia. Now, you might remember from high school physics that inertia is simply the resistance to a sudden change in motion. Think of a ridiculously heavy spinning metal wheel. It physically does not want to suddenly speed up, and it definitely doesn't want to suddenly slow down. It actively stores motion. Well, in the power grid, this exact same physical property applies to the massive heavy spinning rotors inside traditional synchronous generators. We're talking coal, gas, hydro plants. All that stored kinetic energy acts like a giant shock absorber, protecting the entire grid when a sudden, violent electrical disturbance hits.
To truly wrap our heads around why this physical mass is absolutely crucial, we need to look at how that stored energy translates into stability. Let's move into Section 1, the frequency story, and how we balance the grid. Okay, so our power grids have to constantly operate at a very tight, specific frequency, typically 50 Hz or 60 Hz, depending on where you live. This frequency is basically a live heartbeat reflecting the balance between supply and demand. If a massive power plant suddenly trips offline, or say a huge factory just powers up all its machines at once, that balance is instantly broken. Without an immediate response, the frequency drops. And here is the terrifying part. Even a 1% deviation in that frequency can cause sensitive equipment to trip, which can rapidly cascade into a total system-wide blackout.
So, how do we survive those sudden massive drops? Simple. The spinning metal machines buy us time. When a generator trips and the frequency starts plummeting, the physical inertia of all the other spinning rotors on the grid naturally releases their stored kinetic energy. They physically fight the change. The machines do slow down a little bit, but not instantly. They literally buy the grid fractions of a second. And that is just enough time for the automated control systems and governors to detect the drop, react, and restore the balance.
But, as we know, our power grids are undergoing the most radical transformation in a century. We're shifting super fast toward renewable energy. Which brings us to Section 2, the changing grid, and the problem of losing physical mass.
For decades, the whole system relied on synchronous generators. Heavy physical mass, natural inertia, very slow to change. But today, we're replacing them with inverter-based resources, or IBRs. Think solar panels and battery storage. Now, these IBRs are incredible. They're clean, they're entirely software-driven, and they are lightning fast. But there's a catch. Because they connect to the grid through power electronics, they don't have any spinning rotors. They completely lack inherent physical inertia. So while they are totally green, they don't automatically give us that natural physical stability of spinning steel.
To really visualize this, there's a brilliant analogy from the National Renewable Energy Laboratory. Imagine the power grid is a massive tractor-trailer cruising down the highway. The truck and its roaring engine represent our traditional synchronous generators. They are heavily driving the grid's waveform, setting the pace for everyone else. The trailer, on the other hand, represents traditional grid-following inverters from wind and solar farms. They're just along for the ride. They read the grid's frequency and they just blindly follow it. But if the truck disappears, well, the trailer doesn't have a steering wheel. It simply cannot drive the grid on its own.
And this brings us to a really critical turning point for our infrastructure. What happens when the heavy trucks retire and we're just left with a bunch of trailers? Let's look at Section 3, a more fragile system.
Just imagine a low-inertia grid for a second. Say a major transmission line suddenly fails. Without those heavy spinning masses acting as massive shock absorbers, the frequency doesn't just dip a little, it absolutely plummets faster than ever before. So what happens when the grid loses its physical mass? Well, it becomes dramatically more sensitive to every single little disturbance. It becomes a fundamentally far more fragile system.
And grid operators are fighting these exact real-world symptoms literally right now. In a low-inertia grid, the rate of change of frequency, engineers call this roll-off, gets dangerously fast. Our safety stability margins shrink way down. The overall system strength, which is measured as short-circuit ratio, drops drastically, meaning the grid's voltage gets incredibly twitchy and sensitive. And worst of all, protective relays can get confused by the lack of traditional fault currents. They might start tripping unnecessarily, disconnecting even more power, and suddenly you're looking at a cascading blackout.
But hey, don't worry, we are definitely not heading back to the dark ages here. Brilliant engineers are actively building completely new solutions to replace physical steel with incredibly smart tech. Let's get into Section 4, Engineering New Solutions.
So the multi-billion-dollar question is, how do we replace that lost time? Well, physical inertia is instantaneous. It's literally the laws of physics happening at 0 milliseconds. You can't beat that. But to mimic it, engineers are using huge battery energy storage systems to provide what's called fast frequency response, or FFR. Now, FFR can inject massive amounts of power in under 100 milliseconds. I mean, that is incredibly fast. But keep in mind, FFR still has to measure a frequency drop first and then react to it. It's a controlled reaction, not true instantaneous inertia. FFR arrests the fall, and then primary frequency response steps in over the next few seconds to actually sustain and stabilize the whole system.
Which brings us to the absolute game changer in electrical engineering right now. I'm talking about the grid-forming inverter, or GFM. Instead of just helplessly following the grid signal, a grid-forming inverter uses incredibly advanced software to actually establish its own internal voltage and frequency. It can literally synthesize the exact physical forces we used to get from spinning metal. It basically creates synthetic inertia, instantly injecting or absorbing current the very millisecond a grid disturbance happens without even waiting around to measure it first. It's wild.
Building on that truck analogy from earlier, the standard grid-following inverter relies entirely on a strong grid to stay synced. If the grid gets weak, it can lose track and just destabilize. But the grid-forming inverter, it doesn't just survive in a weak grid, it actually injects strength right back into it. By creating its own ultra-stable reference point, a GFM leaves the electric grid in a much better, more resilient condition than it found it. It is literally software replacing steel. The whole goal here is to make the grid feel heavy and stable enough to survive sudden chaos.
Because of all this, today's grid operators are deploying a complete stability arsenal to make sure a 100% renewable grid won't just shake itself apart. We've got grid-forming inverters setting the pace, we have massive battery energy storage systems delivering that fast frequency response, and we also have these things called synchronous condensers, which are essentially just massive free-spinning motors that provide real, heavy physical inertia and short-circuit strength, but without actually generating any electricity themselves.
And there's a truly fascinating real-world example of this arsenal in action right now. Over in the UK, they retired the massive Fiddler's Ferry coal plant, which completely removed its physical inertia from the grid. To fix that weak spot, engineers at the Lister Drive project in Liverpool installed massive synchronous condensers. They basically installed the huge spinning heavy machinery of a power plant, but attached a motor to spin it, using grid power instead of burning coal. The result? Within just 15 minutes of getting a command, this one facility provides 1% of the total inertia needed to safely operate the entire British grid, with absolutely zero emissions. How cool is that? We are literally rewriting the rules of how electricity is managed on a continental scale. Let's wrap things up with Section 5, Keeping the Grid Steady, and look at the big picture. The researchers and engineers leading this massive charge are very clear about the reality of our energy future. To quote the sources directly, we cannot reach 100% renewable generation without modifying the behavior of a significant number of large-scale inverter-based resources to mimic the behavior of conventional synchronous rotating generators. Bottom line, the green transition is entirely impossible unless we deeply respect, replicate, and engineer the invisible physics of the old grid right into the software of the new one.
Because at the end of the day, inertia is way more than just some dusty physics equation. It's our silent time buyer. It's the ultimate shock absorber. It gives the entire system a moment to breathe, a moment to react, and a moment to recover. It really is the quiet, invisible stabilizer holding the modern world together. As we replace the heavy steel of the 20th century with the smart silicon of the 21st, our biggest challenge isn't just generating clean power, it's maintaining the illusion of solid ground. So next time you turn on a light switch and the bulb doesn't flicker, take a split second to thank that invisible stored motion and the brilliant engineers working to synthesize it, keeping the lights on for all of us. Makes you wonder, What other invisible forces in our world are we going to have to digitize next? Thanks for joining me on this explainer. I'll catch you next time.